I make fun of it.
Yes. Thank you everyone for coming or staying after the other seminar. It's an absolute pleasure for me to introduce Nick to you. I got to know Nick as a postdoc when I just finished my PhD and moved to Manchester. I think I was the first, or maybe one of the first postdocs in
Second, I think.
Second postdoc in your group. So that allowed me to see from very up close all the things, amazing things that he's done ever since. And it just makes me very happy to have you here and hear what you've done new from the last time we were together. But so a bit of a formal presentation maybe. So Nick is a professor of chemistry at the National University of Australia and the University of Manchester. And he's a highly recognized figure in the field of molecular magnetism. His expertise, broadly speaking, lies within the theory of magnetic interactions in molecules and magnetic description in molecules, but he has also done quite a lot of work in the modeling of those magnetic properties. And that has led him to want to be the recipient of numerous awards. And for instance, he's the recipient of the Kahn, let me get this right, the Olivier Kahn International Award from the European Institute of Molecular Magnetism, which is basically the highest recognition in the field to his contributions. But he's also a Presidential Fellow of the University of Manchester and a Royal Society University Research Fellow. And he is also an ERC grantee. So yeah, that speaks for itself. And now I'll just shut up and give you the floor. So,
thanks, Danny. Thank you everyone for coming. It's been a wonderful couple of days that I've had to spend here. It's truly astonishing to see the sheer volume of both experimental and theoretical groups working in adjacent areas in these 3 or 4 different institutes. It's actually an amazing place, and I'm really happy that I've been able to come and speak with you all today. So as Danny said, I am currently somehow delocalized between Australia and Manchester. We moved about 1 year ago, so half of my group is still in Manchester, so this is why I'm on this side of the world at the moment. But you will see that we try and bridge this gap a little bit and work all together. So this is Canberra. This is the beautiful city that I now live. It's very small, maybe only 500,000, so not too much different from here. But it really is a lovely place, and this is the university, and the Parliament of Australia is there. And chemistry, I think, is this building here. Anyway, so you're all very welcome to come. If you're in Australia, let me know, and I'm happy to host you in Canberra. Okay, so today we're going to talk a little bit about the work we do in the group over the last couple of years. So we have interests, as Danny mentioned, in magnetic materials. Usually we work in molecular systems, but this is not exclusively so. And more now we're tending towards looking at solid states properties of magnetic materials. But some of our fundamental interests involve paramagnetic MRI, imaging, so looking at how the interaction between nuclear spins and electron spins, both in solid state, but also in fluid solution. We have fundamental interest in actinide spectroscopy and identifying the properties of these kinds of materials and their bonding. We have a lot of interest in vibronic coupling, so the interaction between spins and phonons, their spectroscopy, and also understanding spin dynamics. And I'll talk a bit about this today. And all of that leads towards I guess, 2 areas that we've built up quite a lot of experience in, looking at molecular magnetism, so the single molecule magnets, but also molecular qubits for looking at the coherent properties of electron spins. So I'll start with that side of things, and then we'll move through. We'll have, because I keep talking to people and saying, you'd like this bit and you'd like that, I've added a few things. So I will try and keep to time, Danny, but just kick me when I need to stop. Okay, so molecules in quantum information science. It's a bit of a dirty word, right? Because there are so many other things that are better to host coherent superposition states for quantum information, right? So very well, you all know superconducting circuits. I think you're about to spend some millions buying a big machine that does this, so they work, right? This works. But you can also use trapped ions, right, in magneto-optical traps. You can use defects in diamond, the NV centers, to do coherent manipulation and detection of various interactions. And of course, you can use entangled photons as well. Very different technologies, very different limitations, implementation schemes that you need. everything is up for grabs. And in this context, I think molecules are also a good thing to think about because everything is up for grabs. And so why molecules might be interesting in this space is that as chemists, I'm not a synthetic chemist. I was once upon a time, but it turns out I'm not very good at that. You can make molecules very cheaply in large quantities, right? By purifying a molecular compound, you, by definition, have an identical set of molecules, and maybe you have Avogadro's number. So that turns out to be a very useful thing. You can make lots of qubits cheaply. Again, by the sort of fundamental tenet of synthetic chemistry, they're all the same, right? All these molecules are identical, and they are naturally on the nanometer scale. So this is helpful if you're trying to make some device with 10 to the 9 qubits or something, right? And then, of course, you can think about linking these in some deterministic arrangement, for instance, metal organic frameworks or two-dimensional self-assembled monolayers and these things. We know very well how to do these now. And also, in the molecules, you can control the spin architecture. So which sites host the electron spins, which sites host the nuclear spins, what kind of interactions do they have? And so you have a lot of flexibility with which to tailor your spin system beyond a two-level system. Indeed, you can have multi-level, higher dimensional systems as well. So molecules are interesting. But if we want to exploit the fact that they are on the nanometer scale, brilliant, we need something on the nanometer scale that we can interact with. And usually for manipulating quantum states, we would use microwaves. This is the most common way, using an oscillating magnetic field to drive spin transitions. This isn't great because microwaves have a centimeter wavelength, which kind of means you're limited by that to drive an ensemble of spins. So if you want to drive something on the nanoscale, we need something else. And electric fields here are very useful. And those of you who do scanning tunneling microscopy know incredibly practically that this works and you have a nanoscale control of your electric field. Perfect. However, spins don't interact with electric fields. That's a bit of a problem. So how can we get around this? Lanthanides. So these are the elements at the bottom of the periodic table with F electrons. And the lanthanides in the 4F block have very contracted F orbitals. So they almost retain their atomic-like character irrespective of the environment in which you put them. And so they have a ground state orbital angular momentum with strong spin-orbit coupling that couples to the spin angular momentum. And in this way, you can use the electric field to interact with the orbital component, which is a spatial degree of freedom, such that you can drive spin transitions. And so here's a nice example recently from Ajahn Adavan's group in Oxford, and the chemistry is coming from Eugenio Coronado in Valencia. And so this is a holmium polyoxometallate. I've only showed just the first coordination sphere of this molecule, but we have four-membered oxygen triangles, and above and below we have enormous tungsten oxygen lumps, essentially. But really the important part is this, in the middle. And what they find is that they can do a nutation experiment for the coherent evolution of the electron spin using microwaves and apply a pulse of various duration of electric field. And you can see here that this adds an additional phase to the electron spin, and it's coherent. So it goes away and then it comes back again. So this shows experimentally that you can induce a coherent phase on the electron spin using an electric field pulse. Okay, and what this does, they believe, is that here we are creating a strain in the molecule owing to the application of the electric field, which changes essentially the local magnetic anisotropy, which then induces the effects on the spin. So that's the idea here, that we can physically move the molecule with an electric field to change its spin precession. Okay. We started thinking about this from an experimental point of, a theoretical point of view, and we chose this molecule here. Now, there's no good reason we did, and you will soon find out that that maybe wasn't the best choice, but anyway, this is where we started. So this is a thulium-2 molecule. We have two amides, so these are silyl amide groups, so negative charge on the nitrogen on each end, and we have our thulium-2+. So this is a neutral molecule. Thulium-2 has the same electron configuration as trivalent ytterbium, right? So this is F13. So we have a Kramer's electronic system and therefore an effective spin 1/2 ground state. So we have an isolated two-level system with which we can interrogate, okay? And the important thing here is that we have no inversion center in this molecule. It looks sort of linear, but it's not. It's low symmetry. There's no inversion, because if you have inversion, then all your electric field dipoles cancel. And so you would have no net dipole moment with which to interact with an electric field. But this has low symmetry, so we're fine. So what we did here is optimize the geometry of this molecule in the gas phase using density functional theory, and then we applied an electric field and re-optimized it. And so we're looking for how does the molecule distort under an applied electric field. And so as you see, we apply an electric field along different directions. So X is our vertical direction here along this bond, and nothing happens because, of course, the dipole is almost zero along this direction, right? So nothing happens. If you apply it perpendicular, so either in the Y or the Z direction, it bends, okay? Because you have a dipole and you do that. Makes sense. And when it bends, it also twists a little bit. Okay. So that's fine. There's some structural changes here. But the crucial question is, how does that influence an off-diagonal matrix element between our spin states that maybe we can use to drive a transition? And so we do this by taking the two different structures, the equilibrium structure, and then one that's been distorted by an electric field. And we use a complete active space quantum chemistry method, which allows us to incorporate the the strong static correlation of the F electrons within the F shell, so 13 in 7 active space. And from this, we can understand all of the crystal field splitting of the F manifold and understand how these states are affected by the electric field. We have to also include a static magnetic field to break the Kramers degeneracy because we have time reversal symmetry in zero magnetic field. Okay, so under these conditions, we can now calculate the off-diagonal matrix elements between our ground spin state that are induced by this electric field. And you can see that if we apply electric fields along the X, Y, or Z direction, these are non-zero. We'll first look at the Y, because this is a bit funny. It looks different to the X and the Z, and that's because we're playing along this direction here. And this is the pseudo C2 symmetry axis. And what happens when you apply a field along this direction, an electric field, is the molecule doesn't break symmetry. It stays C2. So things go a bit funny. Whereas along the X and the Z, we break the symmetry. And that's an important part of this. But what's quite interesting here is that even applying a field along the X direction, where we saw no large change in the geometry because the dipole is almost cancelling, we still see strong spin electric coupling. So there's something non-trivial here. And the second part is looking at the magnetic field dependence, which you can see is also got something interesting that we need to learn. So to understand more about the magnetic anisotropy part of this, we just use a simple perturbation expression. So we take the zero field Hamiltonian and we expand the electric field effect and the magnetic field effect as to how this generates our off-diagonal coupling elements. And so looking at here at our static electronic structure, so this is our crystal field splitting of the ground J7/2 manifold, we can see that these are almost eigenstates of Jx. Okay, so this is with a quantization along the x-axis, this linear direction of our molecule. So we have almost Jx functions, okay? And so what that means is that if we apply magnetic field along this direction, we're not mixing anything, right? We're just inducing an energy shift. It's a diagonal term, essentially, in the Hamiltonian. And so these off-diagonal Zeeman elements are near zero, or well, very small. And hence why these red lines, which is the x direction for the magnetic field, are lower than the y and the z, which are higher. So we can understand how these perturbations arise and where the coupling elements come from, and therefore what we need to do in terms of which directions do we choose for applying these magnetic and electric fields in order to drive or generate a strong spin electric coupling. This, however, is really painful to do in practice because optimizing geometries in DFT with applied electric fields is terrible. If anyone's done it, it sucks. And you're limited by the strength of the field you can apply. You have to apply incredibly strong fields, something like 10 to the 9, right, to get things. And that's fine if you have an STM, but if you don't and you're working in, say, solution like Arjang is in EPR, you will be ionizing everything, and that's a problem. So if you want to go to lower fields and probe those, we need another way. And the way we decide, well, my student Will came up with an idea here, which is to make the approximation that we can equate the force that an electric field applies to a molecule in the dipole limit is equal to and opposite to the force that is induced by straining the molecule, right, along some degrees of freedom. So once we optimize the geometry of a molecule, we have the Hessian, which tells us all the forces in all degrees of freedom of how this molecule might move. And if we can equate that with the force applied by an electric field interacting with the dipoles, which we also have in this way, we can find out how does an applied field distort a molecule, right? In a linear low field approximation. And if we do this, we can see that actually we get incredibly good agreement with the direct ab initio optimization. So the dotted lines here are using our low field linear model, but you can see it's in really good agreement with the optimized DFT geometries. So we can do the same thing. I haven't told you about the LBC yet. I'll come to that later, but we have a methodology that allows us to directly obtain Hamiltonians of CAS-SEF quality for different geometries. And so if we put these two parts together, we can then develop these, and here we have the solid lines are our model calculations, so that are in fairly good agreement with these explicit calculations there. Okay. So now we have a way of quite quickly and easily probing the spin electric coupling in these molecules at very cheap costs, right? So these calculations take fractions of a second, whereas the ones doing explicit optimization take weeks. So this gives us a route to doing this very quickly and quite accurately, I think. So what have we learned from this project? So this was published last year in JAX. What do we need? We need molecules that have a large orbital angular momentum in their ground state if you want to have strong spin orbit coupling, spin electric coupling. So use lanthanides. That's rule number one. Number two, we want to break symmetry and cause mixings between our states. So if you have molecules that have a high pseudosymmetry, doesn't have to be exact, but a generally high order rotation axis or something like this, then what you find is as you apply an electric field, you break the symmetry and you start generating really large electric dipoles. So in the equilibrium structure, the dipoles don't have to be big, but it's their derivatives that have to be big. Okay, and at least you get this in high symmetry. And also you get large mixing elements when you break the symmetry. So this is sort of a twofold benefit here. If you are going to do this, you should apply the electric field perpendicular to your symmetry axis, as this will deliver the largest effects in your coupling elements. And the magnetic field should also be perpendicular to the anisotropy of your excited states so that you get mixing into the ground state. This is all just coming from that simple perturbation theory, but it seems to be, it makes sense intuitively that you want to cause a lot of mixing. So these are the rules we've learned. And so most recently, Will has been performing a high throughput study to put these rules into practice and hopefully find some molecules that might be interesting. So he started out by finding all the lanthanide complexes in the CCDC. So these are the small molecule crystalline crystal structures. He then cut them down to only the monometallic ones because we're not interested in thinking about coupling at this point. Okay, get rid of any duplicates or families that are just different lanthanides of the same structure. Okay. Then he evaluated the point group symmetries or effective point group symmetries of these and found a whole bunch that are at least greater than C3. Then he did CAS-SEF calculations on all of those geometries with 8 different lanthanides, looking at distorted and equilibrium structures to get an idea of the spin electric coupling strength. And then this is what we have. So this was on Friday. So I don't know what these dots are. I can't help you with this. But there are lots of molecules there. And these two black lines tell us something. This black line here is the molecule that I talked to you about today, which was picked for no good reason. Just we had it. Okay. This other black line is the holmium polyoxymetallate that Coronado and Ajahn Adavan were looking at, which was quite interesting. But there's a whole lot of stuff that should have orders of magnitude. This is a logarithmic scale with pretty large differences there. So we should be able to find molecules that have spin electric couplings vastly stronger than the ones we've seen already. And that means that either we can perform sub-nanosecond pi pulses using electric fields, or we can use really weak electric fields to do this in a very, very easy way. So I think this is going to be a really interesting area of research, both on the experimental side for people doing this, but also theoreticians trying to hunt in this space. So hopefully we'll find some fun things here, and I can tell you about that next time that I come and visit. Okay, so I'm going to change gears a little bit now and move on to the molecular magnetism side of things, which is a sort of area we've been working in for many, many, many years. So these are molecules that are quite unique. They show a magnetic memory effect, that is a time dependence or a history effect of their magnetic moment without the need for long-range order. So we don't have any interactions between these molecules. This property arises solely of the molecule on its own. And so here you can see just one example, which we call the dysprosocenium cation. And this thing has got some carbon 5-membered rings above and below. These are cyclopentadienyl, if you're chemistry people in the audience. sandwiching a trivalent dysprosium ion. Whoever I was talking to about dysprosium earlier, it really is the best for this, and you'll see why in a moment. But what if you measure the magnetic hysteresis of this molecule, that is, you apply, and so this is an ensemble measurement, but we can prove that it is molecular by doing a doping experiment. So this, or in solution, it maintains this property. You apply a magnetic field at low temperatures and sweep it back towards zero, and you can see that in the zero field regime, depending on where you've been, you have either a magnetic polarization in the up or down direction, and so this is the evidence for a magnetic memory effect. Okay, and this remains open until something like 60 Kelvin in this molecule, which is a nice property. What do you need to see this effect? Well, you need two things. You need a large angular momentum in your ground state. So if you want to make a magnet, it better be a magnetic molecule. That's rule number one. Rule number two is you need a strong, easy access magnetic anisotropy. So that is a single direction in this material that prefers to be magnetized than any other direction. Okay, so easy access, hard plane. That's what we're looking for here. Okay, and if you have those characteristics, we often describe those using these diagrams here. So this is the projection of the total angular momentum, mj, and versus energy. And so if we have the case where our axial direction is the ground state, that is the most favorable direction, it's easy to magnetize along this direction, then we associate those as our largest projections of the total angular momentum. And when the angular momentum is in the plane, that's the smallest projection, and those are our most excited states. And by doing this, we set up an energy barrier that we have to pay if we want to reverse the magnetic moment. So this is now getting towards a classical analogy of the magnetic anisotropy energy, where we're trying to flip this, and it's hard to do so, okay? But this is, of course, coming from a purely quantum origin, right? This is a quantum mechanical system. It's a molecule. Okay, and so the height of this energy barrier, if we can make that really big, hopefully this gets really slow, just like first-order Arrhenius kinetics. If we make the barriers huge, it gets slow. Good. Okay. How do we then design molecules that show large magnetic anisotropy? That's the question, right? We know how to get large spin or large angular momentum. We choose lanthanides, lots of unpaired electrons, orbital momentum, brilliant. How do we design the anisotropy? Well, as I said before, the 4f electrons are great because they are so contracted towards the nucleus. They act as if they don't really care about their environment. That's not entirely true, though, because, in fact, it is exactly this interaction, the crystal field effect, and how their different the anisotropy is generated that we need to worry about. But because they are so shielded, we can think about them as behaving just like atomic 4f electrons. And so it turns out, and this is a beautiful piece of work, we were talking about this yesterday, Nacho, from Sievers, right? This is in the 80s. And this is one of the most beautiful papers, it's one of my favorites. Pure quantum mechanics rules, it's just Wigner-Eckert theorem and Clebsch-Gordon, but you can get analytical expressions for the anisotropic F electron density distributions for the given MJ projections in the ground state. That's a very long sentence, but what it says is, if you choose one of these projections, so the one pointing up or the one pointing sideways, they have different F electron distributions in real space. So for dysprosium, which is the second row down here, if you choose the state that has the largest projection of the total angular momentum, 15/2, the F electrons sit in a compressed sphere. So they would prefer to be around the equator rather than at the poles. Conversely, if you take the smallest projections, that's where the magnetic moment or the total angular momentum is in the plane, or closest to the plane, the F electrons are actually in a prolate spheroidal, or elongated sphere. And so these are opposite shapes, right? Which means that you can totally justifiably use classical electrostatic principles to design a molecule to give you the anisotropy you want. So for instance, in this case, if I was to put two negative charges above and below, I would stabilize this shape on the right, and I would destabilize the shape on the left, purely classically, right? And it turns out that this works incredibly well. So here's an example from many years ago. And this is a dysprosium 3, and we have on the axis tertiary butoxide. So this is an O- with 4 carbons above. There are protons, but I'm not showing those. And then one on the other side as well. So electrostatically, we have 2 negative charges on the one axis. In the equatorial plane, we have 5 pyridine molecules. And chemists out there, pyridine is neutral, right? So electrostatically, this thing does exactly what we want. And so, in fact, this has a very, very large magnetic anisotropy barrier, which is perfect for the kind of physics we want to see. We want to see this large energy barriers. So does that work? Have we made the world's best molecular magnet? No, it's terrible. I mean that with the most respect. These are my good friends. It turns out that this doesn't have very good hysteresis. So other things happen that you need to worry about rather than just massive anisotropy. And so we've been learning this over many, many years. So you see lots of features in here. I'm not going to talk about them, but these big steps are quantum tunneling of the magnetization, which is really interesting. But in general, you have just small hysteresis at very low temperatures. So how can we go beyond this and learn about the dynamics, the spin dynamics, and what's leading to these properties? So now we get into the fun stuff, spin dynamics. We talked about this energy barrier as some imposition on the spin, having to pay some energy cost. This energy, of course, at the microscopic molecular level is coming from phonons, the molecular vibrations of the molecule. And these vibrations induce time-dependent oscillations in the structure, which have an imprint on the electronic states. And so you essentially there have oscillating terms in your Hamiltonian as a function of time. And oscillating terms in a Hamiltonian as a function of time give you transitions, right, in your adiabatic states. So in time-dependent perturbation theory. So we have this possibility now to absorb quanta of energy, to emit quanta, and also scatter. And so these are scattering, absorption, and emission events of phonons, the quanta of vibrational energy in our molecular system. For the physics we need to talk about in molecular magnetism, we need two main ingredients. So the single phonon interactions, where we have these quantized absorptions of phonon energy, lead to these kinds of concatenated processes where we go up and over the barrier. So we absorb a whole bunch and then we spit out lots of phonons on the way back. And this leads to what looks like an exponential temperature dependence. So this is called the Orbach process, and it is really just like going up and over, Arrhenius type kinetics, so hence the exponential. At low temperatures, however, we see something different. We see a two-phonon scattering process, which we call the Raman process, in akin to the optical Raman process. And so this has a power law dependence on temperature, and you can very clearly identify these different regimes in your experiments. So these are the ingredients that we're going to need, 1 and 2 phonon processes. What's the theory? Well, we need to incorporate both the electronic states of the molecule and the phonon states and the coupling between them. So we have our electronic states here represented using a crystal field Hamiltonian. We don't have to do this. I find it most convenient to explain it like this, but you can do it in the absence of a model. So purely ab initio if you want, but we can parameterize our electronic structure in terms of these Stevens operators, which describe the crystal field and its anisotropy. So this is our zeroth order Hamiltonian. Then, of course, we have our standard harmonic approximation of the phonon bath. And then, of course, we have the fun part, which is the spin-phonon coupling. And so here, these essentially take the form of the derivatives of these terms as a function of distortion along some normal mode of the phonon bath, okay? And so, of course, this is an interaction between a whole bunch of terms with all the phonons, okay? So it remains for us to determine these. We'll get to that in a second. But if we have some way of getting them, how do we connect them to rates? There are many, many ways you could do this. You could take the Redfield approach. You could do an open quantum systems, very hardcore spin dynamics thing. Luckily for us, we care about, at this point, just the populations, okay? So we only care about the population dynamics, not the coherences, so we don't need to worry too much. And we can simply take perturbation theory. So this first line here is the one phonon term, which is just like Fermi's golden rule, right? So if you have an oscillating term in your Hamiltonian, you take the square of the off-diagonal matrix elements, and you get something like the rate. But of course, you need to worry about the occupation of your phonons, conservation of energy, and the density of states of your phonons. And you can integrate over the phonon line shapes and then sum up over all phonons, and you get a rate, okay? Fine. The two phonon stuff is a bit nasty, because here we have now two different ways. We're only dealing with one of them, and this is where we're taking the first order spin-phonon coupling. We only have first derivatives here. In principle, you could do a Taylor expansion with second order. We don't have that. That's expensive. We have the first order spin-phonon coupling. And if you take that to second order in time-dependent perturbation theory, you get something that looks like this, which is essentially the origin of this idea of virtual states where you're mixing from the ground to an excited state with one phonon, and then with another phonon comes along and you mix from the excited state to your final state. So you have these intermediate states C that bridge the gap between the incoming and outgoing phonons. Now, of course, though, we have two phonons to integrate over, and it's their energy difference that is conserved with the spin transition, which means you have a whole lot more stuff to worry about, and it's a real pain. So this is numerically a nightmare to deal with, but we've worked it out at least best we can. And so you have all the associated both densities of states. And okay, and this is just a few terms. There are tons. Anyway, there's a good review that we did just a couple of years ago, and Alessandro Lunghi in Dublin has a really good paper on that as well. So practically, how do we get all these ingredients? Well, if we want to get the spin-phonon coupling, we used to do numerical derivatives, where we'd literally distort the structure, calculate crystal field parameters, and take their numerical derivatives. But this is full of noise. It's terrible. The better way of doing it is to do it analytically. And so a very talented student I had, Jakob Stab, who's now in Florence, he developed this method, which is essentially an extension of the linear vibronic coupling approach, where you use the non-adiabatic couplings between states and their gradients in order to get an analytic expression for the derivatives of these crystal field parameters as a function of any degree of freedom in your molecule. But in fact, this gives you access to actually just the Hamiltonian derivatives for any degree of freedom, which is how we could do the spin electric coupling really cheaply, because as the atoms move, we get the matrix elements. So same approach. But then, of course, we're trying to now, in this context, do spin-phonon coupling in the solid state. We care about a molecular crystal. You can't just think about a gaseous gas-phase molecule. That's not helpful. So we need to include it in some environment. And in this context, we want to do CASA-CF to calculate these things. And we're not doing periodic CASA-CF. I would love to try. No, we're here yet. But so we just do a simple electrostatic embedding. So luckily for us, molecules have a natural vacuum gap around them. We can cut them there, and there's no problems. We don't break bonds doing this. And so we can just embed it in an infinite point charge array. Well, we can approximate that by wrapping it, in fact, in a conductor. So we can screen off any artificial point charges that are on the outside of this in this model. So we get essentially the effect of an infinite Madelung potential for this crystal embedded, but it's just one molecule that we deal with CASA-CF. So we have a nice infinite representation of our electronic state with an analytical way of getting the spin-phonon coupling. So that's how we do it. Then we need the phonons. You start writing this down when you're saying, oh, this is what I'm going to do, and you start realizing this is a really nuts thing. This took like, I don't know, 7 years, 10 years, I don't know, stupid, but it works. So here we are. So phonons. So molecular phonons are terrible. If you've ever done phonon calculations on solid state materials, that's hard enough. Molecules are even worse.
You muted yourself for the...
No, it's because that has to be muted. Okay. Because otherwise you get echoes and stuff. You're now famous. You're on YouTube, Danny.
No, you just said you are now muted. And then
it's fine. Right, so we wanted to pick a molecule that was small, right? Because the more atoms you have, the more you have 3 N modes, right? So you need to calculate all of them. So we chose the smallest molecule that we could find. It was the highest symmetry, that had a dysprosium, that had some measurable magnetic relaxation rates that was interesting. And we found this one from Mingliang Tong's group in China. So it's reasonably high symmetry as far as molecules go, with only 128 atoms in the primitive cell, so that's nice. And so we calculate the phonons using periodic DFT, using VASP and PhonoPy. And then, as I've explained, we've calculated the zeroth order Hamiltonian using CASA-CF, and also all of the spin-phonon coupling derivatives using our LBC method. Here are the phonons. It's really dense, right, because you have a molecule, very floppy, so lots of low energy modes of this thing, just subtle twists and turns. But we have our nice acoustic modes. You can see them there, near zero energy and nothing imaginary, so that's nice, but a very dense phonon density of states. Okay. In this context, we were also interested in knowing something about the phonon line widths, because this ends up being a parameter in our model, and we didn't know anything. So we decided to calculate the phonon scattering in this molecular crystal as well, also to prove that our Markov approximation is valid. So this is where, if we want to integrate over the phonon bath and all the density of states, we assume a thermal state for this bath. But no one's really known if that's valid for a molecular crystal. Anyway, we calculate the phonon lifetimes. They're really short, right? So really, this is always in thermal equilibrium compared to the spins. right? So we're totally fine using a Markov approximation, and we can go away and use these line widths, but these line widths you see have huge dispersions, which is something we didn't expect, and we're still trying to work out really the implications of this observation. Anyway, that's for another story. But with all of these ingredients, can we get a simulation? Drum roll, please. Yes, we can. And so the experiments here are from the Chinese group in black, and then our calculations are the two colored lines. No fitting parameters here, just pure ab initio. And so the pink line is using these exact line widths calculated as a function of temperature with all of the spin phonon coupling. But you can see that a fixed line width calculation is also quite a good representation as well. So this is I don't really know this connection yet, how the phonon line width is really being so important here or not. We need to work on this, but nonetheless, we can get a quite good representation of the spin dynamics in molecular crystals. Okay, so now that that's sort of a boring proof of concept, although that still took a lot of work and for us was quite interesting, but relatively boring, let's look at an interesting molecule. So this is very new. This is just up on the Chem Archive now. This is chemistry from Dave Mills's group in Manchester. And this is a molecule that we've been trying to make for a very, very long time, or something similar. Again, we have this bis amide, so two amides on one axis, but this time we have a dysprosium 3 in the middle. And so this is exactly the geometry that we proposed, that we would like to have, right, that I talked about at the start. And the reason this works so nicely is we have this alkene, which is neutral, but it sort of pins this angle to be nice and straight. If you don't have it there, it bends, and then you don't have the geometry you want. We can do the static CASA-CF calculations on the crystal structure. There are two components. It's disordered, so we have to do two, or we can optimize it using DFT. Nonetheless, we get a very large energy barrier, and then we can do the experiments, of course, on this thing. So this is measuring the relaxation rate as a function of temperature using AC magnetometry and actually DC magnetometry at low temperatures. But we can find a very, very large energy barrier to this reversal of magnetic moment that matches incredibly well with our calculations. So this thing, as described, has incredibly large anisotropy, like we hoped. So that's nice. And you can see here the single phonon processes, the two phonon processes, and then at the lowest temperatures, we have this temperature-independent regime, which is the quantum tunneling. So I'm not going to talk more about this bit because we haven't got there yet. But the one and the two phonon processes, we're going to try and model. So looking now just first of all at the experiments of this material, we can compare it to other materials. So on the left here, this new one is in black. What you see is at low temperatures, it's much faster than these other curves. And these are the existing world record holding, blah, blah, single molecule magnets. And so this one is worse, right? By orders of magnitude, much, much faster. However, as you go up in temperature, it crosses over. And up here in high temperatures, it's about 2 orders of magnitude slower. So the spin dynamics have been slowed down in the high temperature regime. And what this means is, well, the hysteresis at low temperatures is nothing special, really quite boring. But as you keep measuring this at higher and higher temperatures, it closes incredibly slowly. So plotting the coercive field as a function of temperature, you have this really slow closing. So up to 100 Kelvin, we have a non-zero coercive field, although it's, some Ørsteds, not very much, right? But theoretically, this is quite interesting. Why does it do this, right? Compared to all the other ones that close very quickly. So we wanted to try and understand that using our theoretical approach. This is where the fun, or I shouldn't say fun, pain, it's probably a better word, started, because this thing has low symmetry, it's big, it's floppy, there turn out to be 4 molecules in the unit cell, and so we have 728 atoms to deal with, and you can see the density of phonons that we end up with this thing. And there are imaginary modes that we just can't get rid of because it's just too big, too floppy, can't do it, can't do the supercell. So, que sera, sera, there we are. But we can show that these are not problematic for our simulations. So doing all of the stuff that I've talked about in detail for the other molecule, I won't go through it again, we can calculate the relaxation rates. And so the purple is our experiment and the black lines are our calculations. So in this solid black line is our single phonon processes, the dashed black line is our 2 phonon processes. And I think you would agree it's pretty good agreement with the experiment. We overpredict the rates in the single phonon region because when we optimize the geometry, it bends more. And so the barrier is artificially lowered in our DFT optimized structure. So this is why the rates get faster, because the anisotropy is less. So we know why that's faster, so that's good. And now can we explain, I guess, the observations compared to the other materials? So we saw before that at high temperatures, it's much slower dynamics, and that's because this molecule in black 1dy has a larger energy barrier. It costs more energy at high temperatures, it's going to be slower. So we understand this. However, it was much faster at low temperatures. So the two phonon scattering events are much more favorable. And you can show that, or explain why, by looking at the spectral density. So this is the phonon density of states weighted by the spin-phonon coupling, which you can see in blue here is much, much larger than this other material in red, okay, which we're comparing to. So it's going to have much more favorable two phonon scattering processes when it's these low energy phonons that are populated at low temperatures. Okay, so that explains why we get faster two phonon Raman scattering. Okay. Then, not satisfied with that, we were encouraged to calculate the hysteresis. I think the words were, they've made no attempt to explain the hysteresis. Nice way of getting a review, but anyway. So we decided that, okay, we'll try this. We should try and calculate the magnetic hysteresis fully ab initio. Well, this becomes problematic because we have huge anisotropy and rates that depend on magnetic field. As you increase the magnetic field, you change your eigenstates and you split the degeneracies of all your Kramers doublets. And so now you open up new relaxation pathways that can happen because you have single phonon transitions that could not occur before when they were degenerate. Now you open up a gap and you can drive them directly. So we have all these other processes that switch on. And so in order to calculate that, you have to do it explicitly. But now it depends on orientation. So this is just one direction that we've calculated here. So we've calculated the one phonon, two phonon processes as a function of magnetic field for a whole bunch of orientations. This is along the easy axis of the molecule. And so you can see there's a huge field dependence at low fields for the one phonon processes. And that's where you're switching on this direct resonant single phonon absorption process. And the two phonon processes you can see have a complicated and not very, it's not well parameterized by a simple model how these scattering terms are affected, but they're non-trivial. And when you take the sum of them, you can see that in general, we get some highly featured results here. And in fact, if you look closely, what happens, these bumps, all these lumps and bumps, that's when we're hitting these resonances in the phonon spectra as we're opening up a gap in our lowest lying states. And so we get these enhancements when we hit these peaks, which is quite cool. But if we take that all together, so that is all of the directions, hundreds of orientations of the magnetic field, as a function of magnetic field, as a function of temperature, we can simulate hysteresis. So this is now assuming that the single molecules are completely independent. So we don't have any many-body effects where neighboring spins flip and therefore generate a changing magnetic field. We haven't done that. It's just isolated molecules, and we're looking at how the population dynamics are propagated through this magnetic field sweep as a function of time at a given sweep rate from the experiment. And so you can see that we get a reasonably good explanation of the features in these experiments. So at the top here, we have this two-coordinate amide compound, which has a narrow hysteresis that you can see quite well. And then we have this sandwich compound that I showed you at the start that has quite a wide hysteresis. And we can model these reasonably well. We don't, of course, have these steps at zero magnetic field because that's the quantum tunneling, which we haven't touched. Okay, so we are missing that for now. But I would say on balance, this is a quite good qualitative agreement between these experiments and the calculations. So can we use this to explain the whole reason this molecule is different and special and has a very slow closing hysteresis? Yes. So with these calculations, we can then plot the coercive field as a function of the temperature. And against the experimental data, you can see that it's not perfect, right? Absolutely not. But it has the characteristic features that we would like to understand. That in this sandwich compound in green here, it drops off very quickly at around 60 Kelvin, whereas in our purple compound, the new one, it carries on nice and slowly and doesn't start dropping quickly until something like 100 Kelvin. And so in this way, we can now explain why this has very small hysteresis that closes very, very slowly. And really, it all comes back to the difference in this energy barriers, that the single phonon processes kick in at about 60 Kelvin here, whoosh, it drops. But they take till about 100 Kelvin before they kick in here. And that's really the origin of the difference in the hysteresis of these materials. Okay. In the last like 5 minutes, because I kept talking to people who were interested in F electrons and D electrons and coupling and craziness, I thought I'd show some crazy stuff. So this is chemistry from Ben Harvey and Randall McLean in the China Lake US Navy lab in California. And they were playing with these sandwich dysprosium and lanthanide compounds as well. But instead of, these are precursors to those other ones. But instead of trying to make the sort of sandwich, they just said, well, why don't we throw potassium graphite at it? And potassium graphite, for those of you who aren't chemists, it's magic dust. It's gold, and it makes materials that have never been made before by throwing electrons at them, just really hard. And so what you do is it just reduces whatever you have, basically. It's incredibly strong reductant. And if you look at this molecule, you will see that it is quite symmetric. In the solid state, you have a twofold, a C2 axis going through the middle. And if you look at the valencies, we have on the bottom, one negatively charged anion. On the top, another negatively charged anion. In the middle, we have 3 negatively charged iodides. So 3, 4, 5 negative charges. We have symmetry and 2 lanthanides. So those lanthanides are, what, 2.5? Well, it turns out that there's a bond. There's a single electron, unpaired electron, sitting in a bonding 5dz squared orbital between these 2 atoms, or ions. And the other electrons are in their F shell. So we have a really interesting situation here where it's a mixed valent half bond between these systems. I'm not going to go through all the spectroscopy. If you have questions, I have some slides, but in the interest of time, I won't go through it all. Suffice to say that the magnetic properties, which were measured in Berkeley by Jeff Long and Colin, are crazy. So the terbium analog, so we've made these for all of them. If you measure the coercive field, so this is a demagnetization experiment. So you go to in this case, using a 14 Tesla magnet, attempt to saturate the thing, and then sweep the field back to zero. Sweep the field back as far as you can, and watch where the magnetization crosses zero. That's the coercive field. And so with using a 14 Tesla magnet, it looks like it's about 14 Tesla. Okay. Well, let's use a 34 Tesla magnet, and it looks like it's about 25 Tesla, or possibly greater. And in fact, I believe they've done this now for 60 Tesla magnets, and it looks like it's about 60 Teslas. So I think it's fair to say we don't understand this at all. How this magnetism is derived. I mean, obviously it's a strong interaction, but this property is crazy. And so we were tasked with trying to understand a little bit about the static electronic structure, and Danny helped in this paper as well. So if we want to understand the anisotropy of these systems, we would love to use CAS-SCF. That's our favorite thing. But we cannot do this for an active space that requires 2 terbiums and a bonding electron, because it's ridiculous. We can do it for the high spin case, but as soon as you try and get a low spin multiplicity, the number of determinants is in the hundreds of millions. I don't know. Computer can't handle it, says no. So we can't do that. What can we do? We decided to determine a pairwise interaction. So that is, cut the molecule in half and think about how the terbium on one side interacts with the unpaired electron, and then build a model Hamiltonian that allows us to build these 3 spin centers together. So that was the approach. So there are some tricks in here, and again, if you want to know the tricks, I'll tell you the tricks. But we ended up building an active space that has just 1 terbium ion and this sigma electron, and looking at the ferromagnetic and antiferromagnetic states of that dimer in the full molecule, and then project that entire ab initio Hamiltonian onto a spin Hamiltonian model, all right? And then we could use that model to build up something of the whole system. That's the plan. Unfortunately, the model Hamiltonian is nasty. And that's because we have orbital angular momentum that interacts with its own spin, and then the other spin, and then the spins interact. And it just gets crazy. But if I break it down, we have a number of terms. The spin-orbit coupling at terbium, localized. The crystal field effect at terbium, localized. Then we have the spin-spin coupling between the radical and the terbium spin. We have the spin-other orbit coupling between the radical spin and the terbium orbital angular momentum. Then we have the spin-spin orbit term, which I have no idea how to explain to you, apart from the fact that it's non-zero. They exist, but I don't know what they mean. So this model Hamiltonian, it looks oppressive and horrible, but all it is an orthogonal spherical projection of any operator that can exist in the Hilbert space of this model, right? And so we can project, this is like 2,000 terms or something, but they're all uniquely determined because they have unique matrix elements and they're all orthogonal operators. So we can project them all uniquely with no uncertainty, right? I mean, of course, we have the uncertainty of the ab initio calculations and all that approximation, but this Hamiltonian itself is a one-to-one model of the ab initio sets. And so by doing so, we can then build up the full picture of the molecule. And now I'm not going to go into all the details because I'm out of time, but we know that we overestimate the exchange coupling because we don't have dynamic correlation. We've just completely thrown this away, basically. So if we downscale our exchange coupling by 20%, which we know from gadolinium is roughly the number, we can then rebuild the full model, which gives us all of the eigenstates of this entire molecule. And we can show the ground state is a stupidly magnetic 25/2 doublet. But the crucial thing is we can compare to experiment by doing this. So the magnetic measurements show that it has an effective energy barrier. So this is going up and over of 1383. And our prediction says, well, look, there's a state there in the middle. That's probably our barrier there. Not bad. Then we have optical measurements. So this is infrared, far infrared magnetospectroscopy. And we can see an excitation at about 284, pretty close to that one, and 446, not too far from those. So I would say that given all of the simplifications, approximations, horrendous hacking together of all kinds of Hamiltonians to make this even vaguely tractable, we've got a reasonably good explanation of what's happening here. And in fact, we've now generalized this to trimers and all kinds of things that, that Ben and Jeff's group are making, and it's really quite a lot of fun. So I will leave it there. What have we talked about? Electric fields. So we've generated models for calculating the influence and coupling of electric fields in molecules and thinking about the rules for designing molecular qubits that might have a strong electric field control. We calculate molecular phonons in molecular crystals. We also do this for amorphous states. And we're able to calculate the spin-phonon coupling with one CASSCF calculation, which gives us the analytical derivatives of the Hamiltonian for whatever kind of parameter you care about. We can get its derivative as a function of phonons, which is nice. Then we can calculate the magnetic relaxation, which is quite accurate compared to experiment. Recently, my colleagues in Manchester have been able to synthesize this 2-coordinate amide, which has the largest effective barrier that we've seen, and open hysteresis, very small, but still open at 100 Kelvin. And we can explain that due to the static anisotropy, but also the large spectral density of the 2-phonon process. And then we've been able to simulate the magnetic hysteresis as well. And finally, just the last thing was talking about these crazy molecules that have mixed valency and d half sigma bonds that gives rise to incredibly strong and very anisotropic exchange coupling. So it remains for me to just thank everybody who's been involved in this work. So the team at Manchester over many years, collaborators in Xi'an in China, as well as the Californian mob, and also some of the people that I've taken prisoner to Australia with me, all of these people for funding, and thank you very much for your attention.
Thank you, Nick. That was great and intense as always. Now time for questions. Yes.
I didn't understand why you need the full phonon spectrum with all the momentum dependence. Couldn't you do just with a gamma only calculation for your model?
People have done this. The problem is all of the phonons are there and they all interact with the spins. Yeah. And the integration of the Brillouin zone is essential if you want to get the quantitative agreement with the experiment. I mean, for instance, one of the original hypotheses of how this all worked going back 30 years was that, that's a terrible picture, so I won't show that one. Yeah, this one's better. Is that it's just the acoustic phonons. And so we're just going to use, some rotational approximation for the acoustic. But this isn't true. All the phonons are important. But of course, the acoustic phonons are non-negligible. So if you want to have those branches and, this Debye-like omega squared dependence, you've got to have them. You've got to integrate across the Brillouin zone. So my argument is always just do it. You know, if you're trying to do it and get the agreement with the experiment, you've got to do it.
Thank you.
All right.
I also have a question. So I found it a bit surprising that this floppy molecule turns out to have a smaller phonon density of states at low energy. Wouldn't you expect that the floppier it is? So if you compare, there was a slide in which you compared, that one.
Yeah.
The red line at low energies.
No. So the red line is dysprosocenium.
Ah, I got it wrong. Okay. So no question.
Yeah. So the floppiness basically means we have lots of phonons at low energy.
Yeah.
And in this context, they couple very strongly to the spin. So, yeah.
Yeah. Okay. Any more questions?
You found terbium in the data that actually from last Friday. You found terbium to be the one that has a stronger spin electric field coupling. Do you have any idea why? So you have many dots in the high.
Yeah.
Terbium, the one which is and terbium actually seems to be magic in many respects. So any quick explanation why?
Well, I find that slide. Yes. Yeah. Yes. You're very right. You've got a good eye. No one picked that out in Florence. Anyway, so here, I think it's two things. Terbium has this similar characteristic anisotropy to dysprosium, where you have the largest angular momentum states having oblate spheroids and the smallest ones having prolate spheroid. And I think it's a quirk of, I don't know, chemistry, but there must be something more basic here, something statistical, that it's much easier to randomly get an axis than it is something like a ring. It's easier to define two things that are closer and opposite one another, and that's way more common than having a ring. And so in this context, you get stronger anisotropy, right? And I think for the reason, and so you see that, say, dysprosium extends quite high as well, whereas neodymium does not. And I think this is the same sort of reason. But terbium is really high because it's non-tramous in its trivalent state, because you have F8, right? And so you have a spin 3 and an L of 3, so to give you a J6 ground state. And so these molecules can have broken non-degenerate states, and also first order spin electric couplings, right? Because you can have these off diagonals appear immediately in zero magnetic field. So this is my guess as to why it is. Yeah.
If I may add another question. So actually, you were just jumping over the quantum tunneling of magnetization, but it's cool effect. You know,
Yeah, super cool. Yeah.
But in this perspective, actually killing your magnetic molecular magnetic properties. So is there any strategy to actually quench the tunneling? Make it larger, or I don't know.
I mean, with the molecular magnetism, the tunneling is coming from opening up an avoided crossing between your lowest doublet, your ground doublet in zero field, right? That gives you this way to adiabatically reverse the spin, right? That's what it is. And this comes from having non-zero transverse magnetic fields at your molecule. And really in an experiment, this is coming from the dipolar magnetic fields from all the neighboring molecules that might be in all kinds of orientations. So strategies people use are to dope and move them further and further apart, which diminishes this. Never goes to zero. But I can imagine that in some way you would need to think carefully about your patterning or your arrangement, your three-dimensional arrangement of the molecules, such that you have this effect minimized.
The single molecule experiments, this should be actually better.
Yeah. Oh, for sure. If you could do that, yeah. Yeah. You should have little to no tunneling. Yeah.
It has been done many times.
Like single molecules experiments many times.
No, the doping experiments.
Oh, the doping.
The decrease of the quantum.
Yeah, but it never goes to zero. Because there's always something in the far field limit giving you a tunneling probability.
Yeah.
But a single molecule experiment, yeah.
Thanks.
Be very cool.
I don't see any more questions. So
maybe one last question, thank you for the nice talk, very nice talk. I was just thinking about, there are no problems at all with degenerate ground states or near degeneracies in these systems, in any of these systems?
In the ones we've shown you, no, but I expect the ones on this slide do, because it's all about having very low-lying excited states that can mix with your ground state under some perturbation. So I think for the electric field control, you want to smash your states really close together so that you've got these really strong effective couplings. In the other systems, no.